A big thank you to all my patrons who support the Engineered Mind podcast. Hi and welcome to the Engineered Mind podcast episode 68. In this podcast we cover topics such as engineering, artificial intelligence, neuroscience, life, and other interesting topics and fascinating ideas to educate, inspire and engineer people's minds all around the world. I'm your host Yusuf, and for this episode of the podcast I am very delighted to welcome Jason Bramburger to my show. Jason Bramburger is an incoming associate professor of mathematics at George Mason University. He has broad interests in dynamical systems, including chaos theory and data analysis. Jason received his Ph.D. in applied mathematics from the University of Ottawa in 2017. Following this, he was the NSERC postdoctoral fellow at Brown University and a PIMS postdoctoral fellow at the University of Victoria. Currently, he is an acting instructor at the University of Washington working in the Brunton-Kutz group at the interface of machine learning and chaos theory. He has also been named a fellow of the Institute of Advanced Study in Surrey, UK for the 2021-2022 academic year. In this podcast, we covered chaos theory, machine learning and how we can use AI to exploit chaotic systems, turbulence, the Navier-Stokes equations and the Millennium Problem, resources to delve into chaos theory, and much more. For updates on upcoming podcasts, AI and engineering courses, and videos, make sure to follow me on Twitter as well as on Instagram. To join my free exclusive newsletter engineeredmind.sh, coming out every Sunday where I share weekly science insights, visit yusuf.substack.com. And now, ladies and gentlemen, here's my podcast with Jason Bramburger. Hey Jason, welcome to my show.
Hey, thank you very much for having me. It's a pleasure to be here.
Yeah, so cool. So we have been in touch for a long time, and today we want to talk about chaos theory and what chaos actually is. But before we jump into the definition of what chaos actually means and how you would define it, can you give us like a 1 or 2 minute bio? Who is Jason and what do you actually work on?
Yeah, of course. Yeah. So my name is Jason Bramburger. I'm an applied mathematician currently at George Mason University. My interests are really sort of like kind of old school dynamical systems. So, asking what solutions to differential equations look like. And more recently, I've sort of pivoted that into or melded it with machine learning, primarily for a selfish reason in the hopes that I can find new equations to work on, right? This is really what's excited me about a lot of this.
Mm-hmm. I think the audience is super well interested in what machine learning has to do with chaos and how you can exploit specific patterns from chaos. But let's start from the beginning. How would you define personally chaos? What is chaos in the first place?
Yeah. Okay. So this is tricky, right? It's you know it when you see it kind of thing, but there's a lot of sort of competing definitions. So let's start from talking about what it isn't, right? Because I think there's a fallacy that sometimes people have where they think chaos is random. Right? They think it's, in a mathematical term would be stochastic, in which case it's not, right? It's not like flipping a coin. Chaos is a completely deterministic phenomenon. And what that means is that, if everything starts exactly the same, and you and I do the same experiment, then we will get the same results, right? So it's not like you and I flipped a coin. But what defines chaos is how sensitive things are to how you start these experiments. So if you start just a little tiny bit off, eventually we're going to get really far away. We're going to get these results that don't even resemble each other. Now, this is what's referred to as the sensitive dependence of initial conditions. This is what people usually use as a defining characteristic of chaos. There are much more sort of intense definitions. So, for example, Bob Devaney in the 80s came up with a list of 3 rules. But then, there's papers out there showing that some of these rules are redundant, some imply each other. And so this sensitive dependence of initial conditions is sort of the defining characteristic, but it doesn't capture everything you see. Now, what I also want to emphasize is just because it's not random doesn't mean it doesn't look random, right? Mm-hmm. This is the other aspect of it. This is why some people get fooled or some people get confused by chaos, because it looks like there's no rhyme or reason to what's happening here, right? If you look at say some sort of time series of coming from a chaotic system, maybe the pressure from day to day or hour to hour in the atmosphere, locally. Something like that, it looks like it's just sort of jumping around randomly. And this is what is extremely complex about it. So you have very, very simple rules most of the time. If you think of maybe the Lorentz equation or some of our other favorite simple chaotic systems, but very, very complex outcomes. That's really how you should be thinking about chaos. Sort of looks random, certainly is not, though. There's a complete separation here.
I see. So would you define the stock market as not chaotic?
No, yeah. So I actually had someone approach me a few years ago asking about sort of consulting along this line, right? So applying chaos theory to the stock market. And I gave them a similar sort of speech here. And no, I think the stock market is fundamentally a stochastic phenomena, right? There are immeasurable components to this that are just completely random, right? You could have the president release a press release about Apple and Apple stock could just drop, right? That's not going to be in any model that we're going to build. So trying to, model the stock market using chaos theory, this was, I think, a pipe dream of the 80s that people really wanted to happen, but has fundamentally not panned out because this is a genuinely, or it's a stochastic system. It's a random system.
Oh, okay, I get it. Yeah, what you beautifully explained, Jason, is this kind of sensitivity to initial conditions, which kind of brings me back to university days when I studied a bit of turbulence, where it's like we have this kind of deterministic chaos, where on one side you have this deterministic system in terms of equations, which are the Navier-Stokes equations in this case, but still they are kind of chaotic because, when you perturb the system a little bit, you can have completely different outcomes at the end of the day. But we'll maybe delve into fluid mechanics a little bit later on. When it comes to the history, I think it would also be very interesting. Like, what would you say are the big names involved in chaos theory? Like, we have the names like Kolmogorov, Lorentz, maybe you can name a few others, and what the contribution was to chaos theory.
Yeah. So a lot of people start the history of chaos theory around 1963 or so with Ed Lorentz giving us his famous equations and the most beautiful image maybe ever produced in mathematics, which is this butterfly attractor that he made on a computer probably the size of the room that I'm in right now that could do less than my cell phone. But I think there's a slight fallacy here, right? We shouldn't start the history so recently. If we go all the way back, say to the late 1800s, with probably my favorite mathematician, Henri Poincaré. At the time, I believe it was the Swedish king offered up a sort of bounty on who can solve these many body problems. So they're old school problems coming from Newton about gravitational influences of bodies in say, the solar system. And, if you only have two bodies, they sort of just rotate around each other, nothing exciting happens. The second you put a third body in there, and that is just complete and utter chaos. It's very, very hard to quantify what solutions look like. So, of course, hardest problem of the day, best mathematician of the day has to get on it. And Poincaré comes in and starts working on this. And I believe he has some grad students working under him, and they're double checking some of his calculations, right? And this is before calculators. You got to do it by hand. And one of them drops a decimal place when they start simulating the equation on paper, right? They're sort of writing down where things are moving, and they get a completely different result than Poincaré got. And so this is really the first observation of sensitive dependence to initial conditions, right? They drop like the fourth or fifth decimal, whatever it happened to be. So you're off by like 10 to the minus 5, and yet still you got fundamentally different results here. Mm-hmm. But the issue with this was, Poincaré observed it, but he didn't have the language or the sort of mathematical technology to describe it. And so, then this kind of gets put on the shelf as a complicated problem, and you have people working on it in the background, but people are getting more interested in, especially after the Second World War, you have people really turning to fluid mechanics. And this is where, as you mentioned, Kolmogorov is coming in. And so then people are noticing similar phenomena with turbulence in fluid mechanics. So you have this sort of similarly chaotic dynamics that is sort of seemingly random and sloshing around, extremely complicated. It's hard to predict. And Kolmogorov comes up with his theory of turbulence that is probably the most widely taught theory for turbulence. That is, you sort of have these large scale structures that are sort of dissipating down into small scale and sort of spilling over and creating like this infinitely fine precision. But the unsung hero, this is about the 1940s. In my opinion, the unsung hero of the 40s, who unfortunately was a little bit forgotten about in this realm, was Hopf. And so people might be familiar with Hopf from the Hopf bifurcation. But what Hopf did is he wrote this paper about 1948 where he conjectured that actually Kolmogorov wasn't quite right. He said, no, actually, these turbulent systems, they have a structure. And what it is that you have all these sort of recurrent states, and they're all sort of tightly compact and wound together inside of your space. And you're sort of flowing close to these recurrent states, but you sort of jump from them randomly. So this is what's known as the periodic orbit, or the unstable periodic orbit theory of chaos. It kind of, again, gets shelved for a very, very long time until about the 80s, when people start thinking about chaos again. And you have people like James York in his, I believe, 1970, 1971 paper, the first person to use chaos to describe what they were seeing in the paper Period 3 Implies Chaos. And this really kicks off the chaotic revolution, leading eventually to things like Jurassic Park, right? And through the 80s. And so this resurgence of Hopf's ideas starts to bubble back up. And people start thinking about what Hopf was saying as opposed to what's been taught, which was Kolmogorov's theory. And people start revisiting Hopf. And this is what I mentioned about Bob Devaney earlier. Bob Devaney's definition of chaos is actually Hopf's description of chaos. And thanks to people like Predrag Sutanovich at Georgia Tech, there's been a ton of work since then that is, in my opinion, vindicated Hopf. It's really shown that, the perspective that Kolmogorov gave us, even though it might be correct, is not particularly helpful. Whereas Hopf's vision, or Hopf's description here of chaos, is really how we should be approaching chaos and how we should understand chaos. I use randomly, but it's deterministic, of course, but sort of switching between, recurrent patterns, these long, coherent patterns that are arising in your space.
Mm-hmm. Super interesting. Thank you so much for the insights, Jason. What I also would be interested in is, you talked about determinism and also pattern recognition. And I think that brings us to machine learning, where this can actually be exploited. Could you maybe give us like a small intro? How can machine learning be used in chaos theory, or like for chaotic systems? That would be super interesting to know.
Yeah. So there's a number of awesome avenues that are being approached through machine learning, right? So as I said right from the onset, what I care about with machine learning is finding models, right? Because if we think about the traditional analysis of chaos, you had mentioned the Navier-Stokes equations. I had mentioned the Lorentz attractor. We have a handful of them, but for the most part, we don't really have that many sort of canonical models. So things like model discovery right off the bat is a perfect way for us to try to understand different aspects of chaotic systems, right? So maybe, the models that we've been working with for a while are just illuminating, one small corner of chaos, whereas, the chaos that's observed in the real world is described by, systems that we didn't really think about. Now, there are some other aspects of this where, machine learning is really helping us to, say, from a practical point of view, forecast chaotic systems. This has traditionally been an extremely difficult problem, and I would imagine you could probably guess why, because of this sensitive dependence of initial conditions, right? This is the old butterfly effect, right? If a butterfly flaps its wings in Paris, do we get a tornado in Houston or something like that, right? This and so because of this, it's very, very difficult to forecast, to predict the output of a chaotic system. And so machine learning is really, really, becoming a powerful tool for learning how to forecast these chaotic systems. And then the other piece that really excites me is that machine learning is really helping us to, extract these coherent structures. So, living out Hoff's vision of chaos using machine learning. We can feed in a chaotic output, and what the machine can help us to do is find these coherent patterns that are coming through, right? So even though it looks like you have complete and utter sort of almost junk coming out of a chaotic system, these machine learning algorithms and these programs that people are using are able to identify, when you're close to certain recurrent patterns and when you have these nice sort of periodic aspects to your chaotic system.
I see. Maybe you can talk about some recent research that you have done using machine learning for these chaotic systems. I think that would be very, very interesting.
Yeah. So this is great. So, as I mentioned, my favorite mathematician is Henri Poincaré, right? So what Poincaré did back in the 1890s or so, as I mentioned, he was working on these many body problems, and what he noticed is, like most chaotic systems, they don't repeat, of course, right? Or else it would just be predictable. I could tell you what's going to happen 100 years from now. But they sort of come back to where they started, right? You think about the weather, right? Every summer we get these, nice sunny days. Every winter we get, at least for me in Canada, we get lots of snow, right? And so, even though it's not, December 22nd is not always exactly the same temperature, you're coming back close to where you started. And Poincaré noticed this as well with these many body problems. And so he noticed, I'm not coming back to where I started, but at least it comes close. And so what you can do is you can instead track what happens as you get close to, say, where you started. So, for example, you take my weather example, just track the weather, every January 1st or something like that, or every first of the month, right? You're sort of discretizing out the weather, and you're saying, okay, a lot of stuff can happen in between, but I just want to know what happens as I sort of come back to the region that I started in. And what this does is this moves you from a completely continuous sort of flowing system to one that will just ask, where did I start and where did I end? And you sort of have this hopping, right? And then you can use the where you ended as the new start point, and then flip over, and you have this recursive process now. So this is called Poincaré mappings. Now, this brings me to what I'm interested in. Is I love Poincaré mappings. I think it is the best way to approach chaotic systems. I think it's the best way to understand chaotic systems. And I don't think I'm alone in this, because if you look back through the literature, going back to the work of James York in the 70s, almost a large swath of the at least theoretical literature is all in terms of these iterative processes. Almost no one is doing a lot of theory on the continuous time aspects. What they do is they slice and they track these discrete iterative processes. So this is what I care about. This is what I like. This is what I'm interested in. I love these discrete processes. This is what I worked on as an undergraduate from an extremely theoretical point of view. And so what machine learning is helping us to do here is, once we collect this data, you have to ask yourself, what are you going to do with it? And it could be extremely high dimensional. Imagine you have a 100,000 dimensional system. I'm going to be outrageous here for a moment, but what are you going to do with that? Even if you could, look at it and analyze it, that's just a ton of data. But what a lot of these machine learning algorithms are helping us to do is reduce the dimension. So dimensionality reductions, boil out sort of what's important here. Sometimes this would be a sort of manifold learning type process, where you're projecting the data onto some low-dimensional surface, or three-dimensional object or four-dimensional object, something that is much less than 100,000 dimensions, right? And then what my own work has done is it has coupled this method of sort of projecting down in the dimensions with a model discovery in those reduced coordinates. So what you're getting is an autoencoder type neural network here, where the encoder function is giving you your projection down from your high dimensional observations. The decoder takes you back up to where you started. And then what you do on the inside of this neural network is you perform a model discovery task. So you can ask yourself, if I'm in my reduced coordinates that are inside my latent variables of my network, what is the iterative process that gets me from one point to the next? Mm-hmm. So you can use a model discovery technique, such as maybe the SIND method, the sparse identification of nonlinear dynamics in here, and that will give you an explicit model. And again, I'm more of a theoretician than I am a straight data scientist. I love having models because that means I can sit down with pencil and paper again, and I can do all of the analysis that I've been trained to do. I can analyze a complex system that might be beyond analysis prior to this because it was just too high dimensional. With this sort of this mapping in the latent variables.
Yeah.
Sorry. Yeah. Pardon.
Yes, I wanted to ask maybe here because when we think about the AI winter, because things haven't been thought of before. Maybe we weren't capable to do things before this AI winter, and now we are with the growing power of like CPUs, GPUs, and so on. Now the question would be, if you apply machine learning to these chaotic system that you said, like, what's the big vision here? What is the end goal, if there's an end goal?
Yeah. This is an important question, right? Well, for me, this is an understanding of chaotic systems, right? So as I mentioned, we have a very limited sampling of chaotic systems. As I mentioned, I could probably name half of the ones that people use. Mm-hmm. I'm not going to bore you with it, but so we have a very limited understanding of chaos in my perspective. We have fundamental, simple systems that exhibit chaos that allow us to, get under the hood maybe with a magnifying glass. But again, it's an extremely limited sample. So what this is allowing us to do is sort of open up the range to much more complicated systems to understand from a from a macroscopic level, what we can expect, how we can understand it, and how we can discover models that actually govern these things. Now, from a mathematical perspective, having an explicit model allows you, as I mentioned, to do all of the analysis that I love to do. And so, for example, you can find out statistics about your chaotic system. You can ask yourself, how much time is it spending near this area? It doesn't seem to be coming down here very much. This is sort of an abstraction in your space, but the idea is you can find invariant measures. Again, all of this requires explicit models to describe your chaotic system. Similarly, with, as I mentioned, Predrag Cvitanovich, he has this entire theory called the periodic orbit theory of chaos. And basically, if you can find these recurrent patterns that live inside of the chaotic system that you're sort of bouncing back and forth between, if you can find those things, you can answer pretty much all of the interesting problems about a chaotic system. You can find out, how sensitive is it to initial conditions. So that's a question about what are called Lyapunov exponents. Mm-hmm. You can find, say, global time averages. So why would somebody care about what a global time average is? Well, if you think about heat convection problems, such as a Rayleigh-Bernard convection model, for example, well, in this case, you have something called the Nusselt number. I am probably mispronouncing that, and I apologize. But essentially, this is asking what the heat transport along a solution is, and it's formulated in terms of a time average. Mm-hmm. So if I'm an engineer, if I'm a control theorist, I want to ask myself, how do I maximize heat transport? I want to make sure that the maximal amount of heat is being moved across this system. Well, what I can do is I can look along this chaotic attractor, and I can see which of these recurrent patterns maybe has the maximal amount of heat transport. And I can use, 100 years worth of control algorithms that engineers and mathematicians and physicists have been working on in order to entrain the system to keep it maybe close to these recurrent patterns where you have maximal heat transport. So there are fundamental, applications of understanding chaotic systems that come from just having the exact model. if you're, as I mentioned, if you're a control theorist, there's a million papers written about controlling the Lorentz systems. It's not because we particularly like the Lorentz systems, right? It's because we have a model for the Lorentz systems. So what machine learning is really helping us to do is, open ourselves up to a data-driven perspective, right? You can collect data, you can feed it through these machine learning algorithms, find explicit models, and with those explicit models, then we can restart, from 50 years ago and start, using all of this theory that's been built up.
Very interesting. I would also be interested in that because I think, or I'm quite sure this question will come up in the comments, is where to get started with chaos theory in the first place. Any books, any courses that you would recommend? I know you have a channel, a YouTube channel, but also Steve Brunton has a YouTube channel where he kind of gets a little bit into mathematical details, how these chaotic systems are built, how the parameters are named and so on. Maybe give us a little bit of insights where people can get started. And also maybe learn about engineering and chaotic systems and the combination of that. And machine learning, of course.
Yeah. So first of all, you mentioned Steve Brunton. So Steve was my postdoc advisor last year. He is one of my heroes, and so I can't say enough good things about Steve, right? So, but Steve certainly has a slightly more engineering focus to his work. So if you're looking for like a mathematical introduction, I immediately have to plug my departmental colleague, Tim Sauer. He wrote just what is almost a Bible of chaotic systems. I can't remember the name of it off the top of my head, but I can post it in the comments afterwards. But what got me into this is Bob Devaney. So he was at BU, Boston University, for a long time. I think Bob Devaney is one of the best communicators who has ever been in science. He has a great textbook. If you want the fine nitty-gritty details of everything that I'm talking about with chaos today, he has a graduate level textbook called An Introduction to Chaotic Dynamical Systems. But if you don't care about all those details, you just want a nice overview, he has a version of that book that's written for undergraduates and high school students. And this was my favorite textbook all through undergrad. I used to just pick it up and read it because it's just so beautifully written. It's so simple. And it's so illustrative of all of the basic concepts that you need to understand chaos. And what I will say to emphasize how much I like these iterative systems, those books by Devaney are always about iterative systems, right? So they're always about these Poincare mappings, hopping back and forth between these points. So that might also help you to really see what it is that I'm trying to do with my research and where the influences really lie. And a lot of it comes from from Bob Devaney's research stream.
Interesting. In terms of machine learning, anything you'd recommend?
Yeah. So I'm not sure if there's been a great treatise written about machine learning and chaotic systems yet. I know that, we mentioned Steve. I feel like he is just writing these fantastic textbooks about data-driven modeling, and I feel like there's got to be one coming very soon from Steve. I know he has a strong influence or strong love of fluid dynamics, so I know that he's had a keen interest in using machine learning there for fluid dynamics, so I imagine there's probably something very nice coming there. But in terms of this, there are people who are doing great work along these lines. As we mentioned, Steve Brunton, Nathan Kutz at the University of Washington. I would like to think myself, but it's still in its infancy for myself. But yeah, I'm not sure that I have a textbook that I can recommend that would give you machine learning plus chaos yet, just because of machine learning is so relatively new in this area.
I think what we could do, Jason, is that you gather like a list of all textbooks that you like and you post it under this podcast with your YouTube channel, and people who see your comment, they can immediately go to your YouTube channel and subscribe to Jason's YouTube channel. I think that's a good idea.
Yeah, I don't want to bury people in reading, but I'm going to try and keep that comment, to a reasonable length. But yeah, also, if to anybody who's watching, please feel free to reach out to me as well, and I'm happy to talk about this anytime, as you can probably tell.
Yeah, you also, I think, started a series on your own YouTube channel, right? Can you maybe explain what it's about? A video series.
Yeah. So I've been trying, as I mentioned, Steve is one of my heroes, right? So Steve has really influenced me, and as you are doing excellently yourself, YouTube is just an awesome way to reach people around the world and let them know about the things that you think are great, right? Or maybe, in my case, it's a lot of things that I just think more people should care about, of course, because these are things that I care about, right? And so I have started my YouTube channel, and there's, as you mentioned, there's one aspect where I'm doing video abstracts for my papers. So these are relatively short videos that just communicate the motivation for the paper, the results of the paper, and where I want to go next. So they're really supposed to be abstracts. They're not substitutes for reading the material, but they are a nice introduction to the subjects, in my opinion. And then what I've also started doing is putting just open source lectures up there. So I want people to have access to the educational material that I'm providing. So currently I'm doing just a Calculus 2 class, so integral calculus class. But I'm going to continue to expand that as I continue to teach at George Mason, and hopefully, allow people to, maybe if you learned Calculus 2 a few years ago and there's some rust there, then you can go in and you can have me explain it to you. Or, maybe if you, maybe you want to learn it all from scratch, right from the bottom. Well, then this is a full open source lecture. Everything will be up there for you to follow.
Excellent. And I will put, of course, the link to your YouTube channel and other resources down in the description, so you can check out Jason. You talked about this iterative system, so I would be curious now, when we imagine now a kind of a mind map, if we classify all these systems, you talked about iterative systems. Is there something else, like in terms of iterative systems, what else would we have when we classify those systems? Also in terms of governing equations, maybe, because when we imagine now kind of a map going into depth, and maybe you can kind of split it up into what governing equations do we have, what kind of system types do we have. That would be interesting.
Yeah. So the first piece of that is iterative systems are these Poincaré mappings, right? So that's primarily where they're coming from. That's primarily why people are interested in them. But of course, most things in life are not discrete. Last time I checked, time flows continuously. And so, most of our models, like, for example, the Navier-Stokes or these Rayleigh-Bernard convection models, they're continuous in time, right? They flow continuously in time. And so this is, another type of place where you would find these chaotic models. But what I'm saying, or what I was trying to get at here, is that you can take these continuous time models and you can ask yourself, as they sort of come back to certain regions, you can turn them into discrete mappings. So you had mentioned this sort of map. I see it almost as like a linear progression, right? Continuous time is what we care about. Mm-hmm. Discrete time is how we can analyze. And so that you have this sort of arrow that points from one to the other. And this is what my interest is not in just these discrete mappings. My interest is using these discrete mappings in order to understand, actual interesting differential equations that are coming up in the real world. Mm-hmm. Can you remind me what the other piece of the question was?
Yeah, that was about the governing equations. And I think what is a good transition is probably a lot of people have seen this kind of Lorentz system, this kind of butterfly-looking attractor kind of system, however you want to define it. I think it would be interesting for you, because I think it would be like a good separate clip, which I can put and refer people to, is how would you define this kind of Lorentz system? What are the governing equations behind this? And why is it always like a butterfly-looking system?
Okay, so
a lot of questions, and now maybe you start with the governing equations.
Yeah. So the governing equations for the Lorentz system are extremely simple. So Lorentz was a climate scientist, right? So he was not coming at this from a background particularly in theoretical mathematics as I would be. But where this actually came from, where his equations came from, they're a really reduced model of convection, right? Mm-hmm. He cared about convection because that's how our weather works, right? Convection drives our weather. And so all that, Lorentz was doing was what I am trying to get machines to do, in a more efficient manner, right? He came up with a very, very simple reduced model. In his case, it's just a 3D ordinary differential equation. I can't remember exactly what the variables are. One's temperature, one's pressure, and the third one I'm missing. But basically, it has this extremely simple system that is supposed to describe, this extremely complex phenomenon. Now, the merits of how much that describes it are fairly loose, but nonetheless, what he was surprised by was how complex these extremely simple equations could be, right? So these equations are just in three variables. They're polynomial. The highest power is 2, right? So this is anybody who took a high school calculus class, working with quadratic functions is not a particularly difficult task. So this might not sound that exciting to you, right? But this goes back to what I had mentioned earlier, is that what we know about chaos is extremely simple rules can drive extremely complex phenomena. And, as I had mentioned earlier, we think of sensitive dependence of initial conditions as being the sort of defining characteristic. But in the back of my mind, the defining characteristic is these sort of simple rules, complex phenomena, right? This is the really, really interesting thing, because, you can give the Lorentz equations to an undergraduate and they probably won't be intimidated by it, right? Because it's not a particularly intimidating looking function. Now, you had mentioned, what is it that makes them complicated? Well, if I had the answer to that, I would love to share it with you. But this is again, this goes back to what I just said. Simple rules, complicated output, right? Mm-hmm. We have the simple rules in the sense of simple physical laws that drive most of our, or that we use to derive most of our equations. We know what the laws are, but we don't necessarily know what the outcomes are. That's driven science for the past 2,000 years, of course, right? Or more. So, being able to say why is a question that I don't think anyone could answer, and being able to predict, what a chaotic attractor looks like at some more than, macroscopic level is nearly impossible. And that's what makes it so exciting, right? That's what excites me about it, is that you sort of never know what you're going to get. You're going to get these really, really complicated phenomena from very, very simple systems. Now, the one thing, if we want to take this back to machine learning, I believe it was yesterday, somebody posted a paper. Again, I'll have to remember what it is. I can post it in the comments. But it's been submitted to NeurIPS this year, where they essentially took, I think it was 131 chaotic systems. So these are the sort of main systems that everybody works with. And they performed a clustering algorithm on them using machine learning. So they basically classified these systems based on how they behave. Mm-hmm. And I can't remember exactly what the results were, but you basically saw there's really only 5 or 6 clusters where things sort of, a lot of systems look like Lorentz. So that seems to be one sort of prototypical kind of chaos. A lot of things kind of look like the Rosler system. So again, that's another kind of prototypical chaos. And, so this tells us that, maybe chaos has a relatively simple classification. And by that, I mean, we could put it in little bins. Mm-hmm. And the truly amazing thing about this is, you can find the same phenomena that drives really chaos in say the Lorentz system. You can find that in fluid models. So there is a universality here, right? There is a purpose to studying simple systems. And that is because, these relatively simple models seem to be behaving in the same way as, the models that most people really care about, things like the Navier-Stokes equations or something like that.
Now the question would be, if we use deep learning or / machine learning, can we win $1 million by solving one of the millennium problems?
I knew this question was going to come up, So I will say no, and I have a rant that sort of comes with this, right? So So the question of Navier-Stokes existence and uniqueness is the one that you're alluding to. This is a millennium problem. You can get $1 million if you can prove global uniqueness of solutions to the 3D Navier-Stokes equations, or if you can disprove it. So you can find a solution that is not, it doesn't exist for all time. Okay, so this, knowing if a solution exists does not tell you anything about how the system behaves. Right. So the traditional, the methods of showing that solutions exist are like old school, pencil and paper mathematical methods that you sort of, you have to write a contraction mapping and you show that it converges and all of this kind of fun stuff that maybe anybody took a differential equations class in grad school has seen. But okay, so let me give you a example of this. We talk a lot about the Lorentz systems in this video. So the Lorentz systems are known to have a solution. They have the existence uniqueness property that everybody wants for Navier-Stokes. But does that tell you how the solution behaves? Of course not, right? Or else we would have a complete and understanding of Navier-Stokes. So, people talk about turbulence, which to me is really sort of chaos in fluid models. People talk about turbulence and the sort of $1 million prize problem sometimes as being related. And I think that is a misconception. To me, they're not related. They are two fundamentally different problems, because if we know solutions exist, it still doesn't tell us what they look like or how they behave.
Yeah.
And so, these are, turbulence, traditionally probably the oldest problem in physics that's completely unsolved, I suppose, or at least one of. And we're not going to have an answer to how turbulence behaves. If we can win ourselves $1 million solving this.
Too bad. Yeah. Let's see. Maybe someone can crack the problem. Yeah. At least you have a good insight.
I would love to be wrong, right? I would love to be wrong with this, but this is my personal opinion, and it comes with, I've been doing math for quite a while. I think I have a pretty good grasp on this. What I will say, when people talk about the $1 million prize, so it seems that the community is fairly split on whether or not this millennium problem is true or not, right? So sometimes when if I'm talking to fluid dynamicists, I like to do like a little informal poll. I say, do you think it's true or not, right? And unlike some of the other $1 million problems where we think that they're like obviously true or obviously not true, they're just too hard for us to solve. This one seems to be genuinely split through the community, right? It seems that some people think that it's true, and then just as many think that it's not. And this is really, really fascinating to me because, there is an aspect independent of chaos that this would imply, in my opinion. And the thing is, people use the Navier-Stokes every day, right? We use it to design aircrafts properly, for example, right? There are massive consequences to using the Navier-Stokes equation. So if we can prove the solutions exist and are unique, well, check that one off. We got a good model. This is, things work. Mm-hmm. But to me, it's much more detrimental if it turns out that their solutions don't exist, right? So if we can disprove this millennium problem, because to me, that tells me that our model is flawed, right? We got to fix the model, right? We've been working with a model that seems to be, pretty close to correct because we've been using it, like I said, to design airplanes. But what this is telling us is that there's a flaw in the ointment, right? We have something that needs to be added or subtracted from those equations that is very minuscule, but it makes them properly describe nature. Because last time I checked, right, the wind doesn't flow and then develop a singularity and suck us all in or something like that.
That's right.
So, yet, of course, right? So
yeah, this is so interesting that you said that, Jason, because I recently had someone on the podcast talking about this equation F equals ma, so the classical equation that we all know, but he said that it's also incomplete. It's an incomplete model, but it works because it's not taking into account second law of thermodynamics, for example. Because, well, we know when we kick a ball, it eventually stops at some point, but the equation predicted it would basically go on and on forever. But then we don't take into account like dissipation of heat and things like that. So also entropy plays a huge role. But maybe you're right. Maybe we use a model that seems to be right, but maybe there's something missing.
Yeah. So I, as mathematicians, this is what we do, right? These are, again, bringing it back to machine learning, this is the old school reduced order models, right? Mm-hmm. This is, if I had to, pay attention to every physical law when writing out an equation for something or deriving, Maxwell's equations or Navier-Stokes equations, right? There might be very, very little friction, but technically I should have maybe friction in some of these models or something like that. And, what we've learned from, centuries of mathematical research, at least since Newton, is that, we are very good at figuring out what we need and what we can dispose of. And I think that this would be sort of similar to Navier-Stokes because, I keep using this example, but we use it to design aircrafts, right? Like this is an extremely important aspect of this. So clearly, most of it is right, even if there are little issues that might be, on a more mathematical level.
Yeah, that makes complete sense. And I appreciate that you went in so much depth. And I think people have now a bit more understanding of what this Millennium Prize problem is all about. It's not about solving the equations, right? I think a lot of people think that the Millennium Prize problem is actually solving the equations, what we do on a day-to-day basis, or like even on graduate level using, I don't know, any software. When it comes to mathematical challenges and maybe boundaries, I mean, you talked a lot about them during the podcast, but maybe to wrap things up, is there something that's extremely difficult maybe also to describe mathematically and even using machine learning, but maybe you have hope that this might be solved in maybe 5 to 10 years, if it's even possible?
Well, okay, so turbulence, right? Turbulence is, as I said, it is the unsolved problem in pretty much all of classical physics, right? Am I optimistic it's going to be solved in the next 5 years? Absolutely not. But the other aspect of this is, what does it mean to solve turbulence, right? It's not posed as a proper question. What is the integer between 2 and 4, right? Like it doesn't have a direct answer, for example. So what I'm extremely optimistic about and is that, we can use machine learning to increase our understanding of turbulence, develop reduced models for turbulence, and even take these very, very high dimensional fluid equations. In these cases, they're infinite dimensional, and use machine learning to treat them like they're the Lorentz equations, right? As I mentioned earlier, the Lorentz equations are low dimensional. They're pretty well understood, at least, what the attractor looks like and what's going on in it. And I said that we're kind of seeing the same things coming up in some fluid models. But the question is, you have this big question mark in the middle that says, how do you get from one to the other? And so this is what I'm truly optimistic about machine learning doing, is saying, okay, I can find that correspondence, right? So I can get you from simple to complex and back again. This is what I really think could be great for the community, because on pencil and paper, there's just no way I'm ever going to be able to come up with that, right? It's just not part of the current mathematical techniques. And so maybe in 50 years, somebody will come up with a way to do it. But what we're seeing now with these modern computational techniques is, this is what excites me about it, is that it's allowing me to do things that could only be done on paper prior to this, or could hardly be done on paper prior to this, right? So you can say on paper, this thing exists, but no one really knows what it looks like. This correspondence maybe exists. Well, what machine learning is allowing us to do is find these correspondences. It's allowing us to, going back to that NeurIPS paper that I just mentioned, it's allowing us to classify things that look wildly, wildly, wildly different in on paper, turn out to be very, very similar. And this is what I'm most optimistic about. And I think this is what a lot of the sort of the chaos intersected with turbulence and machine learning and fluids community. I think this is what excites a lot of people here, is because it'll give us a method, to understand things that were previously not well understood.
Very interesting. Jason, I know that we have a lot of people from the audience also being very young, like 14, 15, 16, maybe 17 years old, starting very young. When they want to start with one system and exploit kind of the characteristics, learn a bit about chaos theory, should they maybe start with a physical double pendulum? Do you think that's a good starting point to maybe get a grasp of what is chaos?
Okay, the physical double pendulum is awesome to watch videos of. So it depends on how you want to approach this, right? Mm-hmm. Do you want to check out cool videos? By all means, right? Play with the double pendulum. I had mentioned Jim York earlier in the talk. Jim York used to give talks with the double pendulum in his pocket, and he would pull out the double pendulum and he would show everybody. Then everybody knows what chaos looks like. But in terms of, if you actually want to like get your hands dirty, and I mean this like in the lightest possible way from a mathematical perspective, definitely not the double pendulum, right? That's still an extremely, extremely complicated system. If you want to do a chaotic experiment on your calculator, or if you're watching this on your computer right here, pick a number between -2 and 2. Okay, I don't care what it is. Pick anything you want, square it, and subtract 2. So your function is going to be x squared minus 2. Whatever you got out, do it again. So, whatever you got, you put in your number between -2 and 2, you square it, you subtract 2, you get a new number. Restart the process with that number. And then get do this over and over and over again, and get your friend or run the experiment again by yourself with a starting number that's very, very close to what you started with, but not the same. So if you started with 0, run the experiment again with 0.000000001, whatever you want it to be. Super, super close to the point where if I was looking at it on paper, I'd say that's basically 0, right? You'll get to observe sensitive dependence with initial conditions or 2 initial conditions just right on your calculator. That's the best function to start with. And that's what, sorry.
Is it the logistic map thing?
Essentially, yeah.
Okay,
yeah.
Good.
Yeah. So the logistic map technically is x times 1 minus x. But it's a quadratic function, and just to make the discussion slightly more advanced, to bring these two together, all quadratic functions. So they're one hump functions, like either way. Feigenbaum gave us a universality result that says they all sort of behave the same way. So your logistic function and my quadratic function, x squared minus 2, they have the same characteristics. They are the same function, just viewed in a different coordinate frame.
Oh, that's interesting. Didn't know that. Yeah, that's so cool. Yeah. I learned a lot during this podcast, Jason. Thank you so much. Maybe to wrap things up, any last motivating words, or maybe where people can find you, and also what you would tell them when you want to motivate them to maybe go into chaos theory and maybe help the community to take a step forward?
Yeah. So my word of advice is we need good mathematicians working on this, right? This is, as I've tried to say this many, many times. Turbulence is extremely important. We need to have some way of understanding this and some way of integrating machine learning, right? This is maybe some people don't think that this is the best method for this, but in my perspective, it's the only game in town right now, right? Because 200 years of mathematical research hasn't got us that far into turbulence. And so, my advice is, if you're interested in this, just come work with me. Come work with many of the other people in the field, like Nathan Kutz and Steve Brunton. There's tons of work to be done here, and there's tons of room for people to shine as great mathematicians. My advice would be, you're going to have to learn a lot of pure mathematics, so topology and all of the fun stuff, analysis, all of that, all that exciting pure math. So we need people with strong mathematical backgrounds as well to come at this, because there's one thing where you can sort of implement these things blind, and maybe you're not quite sure of what you should be looking for or how to analyze the system that you're getting out. And so this comes at a slight detriment, right? So having a strong background in mathematics to start with, and then getting into this a little bit, will really be to your benefit, because I see, where my interests lie and where I think a lot of the community's interests lie are really at the intersection of computation, which is machine learning in this case, and actual, pen and paper mathematics. So it's not, with only, only math, maybe we're not going to be able to do much, and only machine learning, maybe we're not going to be able to do much. It's that Goldilocks zone in the middle where we need people.
Excellent. Beautiful ending, Jason. Thank you so much again for being on the show. I learned a lot, really. There was an excellent podcast. We talked 1 hour on chaos theory. We probably could have gone on for like 1 more hour, 2 more hours. But I would like to have you on a second part, maybe in a second part on my show. So let's see how the audience reacts to this one. I think it would be very, very doing well in the future, for sure. And I will put every relevant link down to your channel, to all the books in the description. And please comment under the video, Jason, so people can find your YouTube channel as well. And with that being said, thank you so much again for joining the show, and see you around on Twitter, I guess.
Thanks for having me. I had a great time.
Thank you.